To another episode of Uncertainty and Probability Theory, the Logic of Science. We're up to class 69. Instead of doing control, I got some good questions. I've got this question in various forms one way or another, but somebody put it very well at YouTube last week. I think it was last week. And I'm going to read that question out to you in a minute. We're going to do that. And it concerns models. Since we're on models now and this kind of thing, and parameters of models. Why? And I titled this, Why Parameters Don't Exist. Well, because distributions don't exist. And because probability doesn't exist. None of that stuff exists. These are all matters of our mind. But somebody asked us, let's try to remember. We wanted to know future GPA. Future GPA of whatever this situation was. We got this data from some schools, a couple hundred observations, and we had a race marker, white or non-white. And so we used a normal distribution, and we gave a parameter for whites, and we gave a parameter for non-whites, and we gave them, these are the central parameters, and we gave them a shared spread parameter. And the reason is because everybody does that. Sometimes these are mistakenly called the mean and the standard deviation, or sometimes the square of this is called the variance. These are terms I think should be deprecated because they give the idea that this particular population has a mean. Now, in a sense, it will, and it leads into our question, which I'm going to get to. So let's just try to remember this. We did it the right way. We did it the right way first. We calculated the probability we would see any particular GPA we liked in the future using this model, suitably discretized, and given the old data that we have. And the reason we used this model, we knew it would be wrong, but we knew it might be useful in an approximate sort of way, and that seemed to be the case. There was some probability leakage, which I'm going to cover again in a minute here if you don't remember what that is. But perhaps we thought, at least for my purposes about GPA, which I don't really care about, especially in an era of great inflation like we have and so forth, it's not a very meaningful number anymore, so I'm not that interested in getting that precise about it. Although students might still try to grade grub and all that kind of stuff, to me it doesn't mean that much. So the errors that we had in this model aren't that significant. So, and in the wrong way, remember, we produced estimates. They call them estimates for these parameters, and we put little hats on them. We estimated these parameters, and this one we just kind of ignored. This one we ignored. We were interested in the uncertainty in GPA, but in the wrong way, we forget all about that. We don't care anymore about the uncertainty in GPA. We care about what we consider causes, in a sense. As long as our correlation gives us a wee p-value, we're then entitled to say the cause we thought of, and nobody else's cause, but the cause we thought of is operative, and chance did not, whatever the heck that is, did not cause the data, and instead our cause did, and nobody else's cause did. Now we saw that that's preposterous, but that's what people do. So we give estimates of the so-called true values of these particular parameters. And now we know they're not true values in this case, because we did, in the right way, we had from 0 to 4.15. 4.15 was the maximum GPA that we could have in the particular data set. And for whites, for instance, we saw that the model predicted something like this. We had, I don't remember what it was, 2% probability for whites of having grade points greater than 4.15. Whatever. I mean, that's, for my purposes, that's close enough. For your purposes, it might not be close enough. That's something you have to decide on your own. If you have models that have this kind of probability leakage, maybe that's important. Maybe it's trivial. That is not something any statistician can decide for you at all. That's something you have to decide. There is no marker. I can only tell you that there's this much leakage. There's no acceptable level, and I would forbid, if I could get away with this, forbid anybody to compiling such a table of this is acceptable leakage and this is moderate leakage and all that kind of, none of that stuff we should do. This is just the way it is for this particular model given this data. And it's all conditional leakage too, just like probability is leakage. We change one data point, we add a data point, we subtract a data point, we add or subtract a data point in our numerical integration. This probability leakage can change. It's all conditional. All probability is conditional. All logic is conditional on the arguments and evidence and premises and assumptions that we bring to the problem. Okay, I have to repeat that over and over again because once we start getting into this model stuff, it's too easy to think there really are true values of these parameters. And there can't be. And so there can't be in this case because there's probability leakage. And so there can't be true values of probabilities of impossible values. So here we and I did say that we put hats on these things here. That's just custom tradition, nothing wrong with that, to indicate we've given a fixed guess for them. And then we calculated those things called confidence intervals, and we saw how silly those things were too. Okay, now here's the question. I'm going to read it to you. That's why I'm holding this thing up here. Would it be reasonable to say that those hat parameters are estimates of the true parameters, also in quotes, because they are calculated using only a subset of all the possible data that I could collect? Very good point. So I could say that these are only estimates of the data given I'm only measuring a subset of everything that I can measure. Where the true parameters are the ones that are calculated with the full data set. Okay? I say, this is the person going on here, I say true parameters in quotes because I agree that they do not inhere in the data, but because the true refers to the full complete data set rather than just a subset. Now, my heart soars like a hawk because that's a wonderful question. It makes me very happy to hear a question like that. The answer is no, but it's a very good intuition. So let's go through a couple of examples to see why. Well, we see why it's not the case in when we have probability leakage, but there may be cases in which we have no leakage. This only occurs in certain things, and it doesn't necessarily occur. We don't notice it occurring in other things. So let's look at a more common version of this in which we have a poll. And voting polls are a good example of this. We have a poll, who are you going to vote for president? Or who do you think will win the presidency or something like this? And we know there's only a fixed, there's a poll. And we know that there's a fixed number, n, and n is going to be less than infinity. These are known facts about the world. We might not exactly know what the value of n is, but we know n is there and n is fixed and so forth. And I give the example in the write-up. Suppose we're going to measure right now all the adults alive right now who are 18 or older in the United States and are legal citizens, born here, all that kind of stuff, whatever you want to say. Not those to come, not those in the past, just those that exist right now. There's going to be n of them, whatever n is, I don't know. And I'm going to ask whether everybody meets the criterion of having an inch, a nose of majestic 1 inch or greater or longer. Okay, that's our criteria. Do they have a big nose or do they have a small nose? That's our criterion. And I can estimate a subsample of that, and I'm not going to be able to measure everybody. And the question is, I could have a parameterized model of this, and can I not say that that parameter is going to be an estimate of the true value once all the data is in? Now let's see why that's not the case. First of all, it's a terrible thing, unfortunately. People will say the probability of the criterion, I'll just put it at C right here, and this is the wrong way. And this is the wrong way of doing things. They'll say the probability of the criterion is theta, say some parameter theta, or whatever parameter we like to use. So they'll use a p or something like that. They'll say that's the parameter. We don't know what the parameter is, but we can make an estimate of that parameter. And again, this is the problem of naming this thing the probability when it isn't. It's a parameter representing a probability. We don't know the value of the parameter, therefore it's not the probability of the thing of interest. It's it's using the term twice, and we have an equivocation fallacy that sneaks in unawares. Same thing with these things up here. Okay, so let's suppose, first of all, that we have measured everybody. Let's suppose, first of all, and just for the sake of argument, it doesn't matter what numbers we use, but let's suppose we have 300 people. That's our entire set of data that we're going to have, whatever it happens to be. And we'll suppose that 200 people met the criteria for whatever it is that we're measuring, the voting or the length of the nose or whatever it might happen to be. There's nothing wrong with this being such a small number, 300. We can make that 3 million or 3 billion or 3 trillion or whatever we like. Whatever number we like, it will be less than infinity. That's no limitation, as we saw when we talked about infinity a million years ago. We could have numbers that are just unimaginably large that are still an infinite distance from infinity. And so we'll never exhaust, our particular thing. Okay, so now we could say the estimate now is going to be 200 over 300. Now that is a reasonable thing to say for an estimate. If all we knew, and we're going to turn a blind eye to the actual measures we have on all 300 of these people. We've made measurements on all of them. That's how we know there's 200 of them. But suppose I know what the measurements are and you don't. And I say all I can tell you is that there's 200 of them with the criterion, 100 without. We know there's 300 altogether. And therefore, we can deduce the probability of any one of the individuals in this 300 has a probability of 2/3 of having the criteria. Simple, right? But if we, because this is just an estimate, I could form a confidence interval around it. I can form a confidence interval. I did that. I forgot the exact numbers. So I'm going to peek here. It's 0.61 to 0.72. 0.61 to 0.72, and this, of course, equals 0.6. So what does this confidence interval mean? Nothing. It doesn't mean anything. It's a preposterous confidence intervals for the first place. If you remember confidence intervals, your confidence interval, a confidence interval you calculate right now for your thing, has no interpretation other than the true value of the parameter is in it or it isn't. The width means nothing. You can't infer any probabilities about a true value of the parameter being in or outside the confidence interval. There's no certainty or uncertainty involved with it. All you are allowed is the tautology, so which is why everybody treats them in the Bayesian way, which we have not yet come to, which we will. But the Bayesian way says, I'll just give you the sneak peek, says there's something like a 95% chance that the parameter, the true value of parameter, will be in this interval, which is also false. The Bayesian way is also wrong. There's a 100% chance that the true value is in this particular interval, 100% chance, because we know the true value is 0.666. In any case, this isn't the parameter, it's a count. It's a count over a known number. Everything here is measurable and observable. Now, what we did when we did the right way, if I can find my eraser here, when we did the right way, remember, if all we know there's going to be, and we did this in the origin of parameters. I'm going to have a link, but you can go back and look at the old stuff. If we know, and this is all we know, and nothing else, I'm not even going to tell you what forget the nose criterion, I'm not even going to tell you. People either have this criterion or they do not. All right, they actually can measure this criterion or they won't measure this criterion, and all the people we're going to pull. We know there's going to be n of them, and n is necessarily finite, okay? That means we could have 0 people meeting the criteria, 1, 2, all the way up to n. We did this before. And the probability that the number of is going to be I, whatever this is matching the criteria is I, given this n and the information we have is, of course, 1 over n plus 1. We can deduce this. This is the probability a physical number of people, a physical number who are going to match this criterion exist, m equals I, where I equals, of course, 0 to n. The probability that m equals I, given this information, is 1 over n plus 1. We can make a prediction right now of all those, we can make a prediction of what we're going to see. Of course, if we have more information, for instance, if we're talking about person's nose lengths or something, whatever we want, we could add more information to this. We could add and the probability would duly change and so forth. But right now, before taking any observations, we could still make predictions. All right, it's crucial to understand it. We can still make predictions. There is no parameter. No parameter yet exists. This is all just things that we have deduced. This model is wholly deduced just from the information that we have, and there's no parameters, nothing like that. Now, suppose we take just one observation. We take just one observation, and n is some number. N could be just one. N could be any number greater than 0, integer, of course. But let's suppose n is somewhat large, 300, whatever you like. It doesn't make any difference, though. If I take just one observation, then we saw in the, and we'll call our sample of size W, which will have a certain number who met and then didn't meet the criteria, didn't meet the criteria. There'll be a certain number in there. This will be a certain size W. We could just take one. So we'll say W equals 1. Then we saw we could calculate the probability, and there'll be n. That tells us necessarily we have n minus W observations to come. We can calculate the probability that there'll be however many to meet the criteria in this n minus W, or we can compute the probability that there'll be a total of them, including the ones we measured. We can compute anything. We can compute anything we like, any kind of question we want about the observable data in the right way. And there's no parameters in any of this. Everything is just measured. And we saw how we can deduce all of these things. We also saw that if we let n go to infinity, this model becomes approximate. And we can find a parameter when we let n go to infinity. And then that model becomes useful or not useful depending on the purposes to which we'll put it. We still have to do all the other tests we haven't learned how to do and so forth. But that's how parameters originate, by assuming things all of a sudden go to the continuum. All right? Now, let's continue this example. But this, I can take no observations, I can make predictions. I could take just one observation and I can make predictions. I could take all possible observations and I can still make predictions. Doesn't matter because there's no parameters, everything is physical. But let's do the wrong way here. Suppose I took just one observation and the observation was that the person met the criteria, okay? Then the estimate will be, I took just one observation and the small n equals 1, then the estimate will equal 1 with a confidence interval of 1 to 1. Suppose instead that I took n equals 1 and the estimate n equals 1, but the person did not meet the criteria. Then the estimate is 0 and the confidence interval between 0 and 0. You can't really do it. I mean, these are absurd numbers to do because if you're going with the parameters, those parameters, if you parameterize the model in the usual way, that we did, using this argument that the probability is this parameter and not just a parameter, to use that equivocal language, then we could certainly calculate things. If we just take one observation, they'll say, well, you can't just make one observation. You got to take a lot of observation before this stuff becomes valid. No, you don't. If the theory works, the theory works. If the theory says, here is how you calculate a confidence interval, here's how you calculate an estimate, and here's the expectations we're going to have and so forth, then it must work. This just works. The right way just plain works. Just works. No matter what we're going to ask. We can ask any question about observables we like, and because we have deduced everything, and there's no continuum bound parameters in here. But for this, it becomes absurd. It becomes absurd. It sort of makes sense in the middle. Maybe we could have these parameter estimates if we're taking only a sample of 20, say, and we get however many we're going to meet the criteria and so forth. And it's starting to make a little bit of sense. But it's still forgetting what you wanted to do. You didn't want to know the parameter. What you wanted to know was the proportion, which is not the same thing. The proportion is you wanted to know there were 200 out of the 300, that were going to vote a certain way or met the criterion. You didn't want to know the probability. Nature, the way they say this, nature is drawing things from a distribution with this particular probability. Nature is doing nothing of the kind. Nature is never drawing from a distribution. You'll see that language used all the time. It is not the case. There are causes in operation, and they can be entirely different causes and so forth in each of these observations. What makes everybody's nose a certain length there? What makes them vote a certain way? All that kind of stuff can have a myriad of different causes, all right? So nature is not drawing any kind of numbers from distributions or something like this. So these estimates don't even match, even if not before we've taken any data, not when we take a little bit of data, and not when we take all the data. And the same is true in these more continuous-like things. Let me erase this, I guess. Oh boy, this is making a mess. Let's go back to the GPA kind. Well, we won't go to the GPA. We'll go to some number we think that there's no obvious probability leakage. We could have temperature has a natural absolute zero. I don't know, difference in income or something like this, where we could have numbers on either side of zero. And when it's not obvious, we could have differences of income. Income seems to be potentially infinite or something like this, and we're going to have differences in income between this set and another set, whatever that happens to be. We could have numbers. But in the end, in any real example, n will still be less than infinite. And this is absolutely no bar to us. This is absolutely no limitation. You can let n be n equals 10 to the 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 10. All of this, e to the 10 to the 10 to the 10 to the 10. And you can keep going, say 1,000 times. And that number will still be less than infinity. It'll still be infinitely far away from infinity. It'll be incomprehensibly large. But it'll be absolutely no bar to our thinking about it philosophically. And it's still finite. We don't need to worry about the continuum or anything like this, or any of those difficulties that crop up, whatever that's going to be. Still finite. So, but in the end, we'll have a picture for these kind of things. Suppose we take, these are counts. These will be counts. Whatever it is, counts. And this will be the something like this. Here will be our final. We've got everything. This is the population, absolutely everything that exists or will exist. Now, we don't know this. Okay, we don't know what it is in advance. Obviously, if we did, we wouldn't be doing any of this stuff. We would just state it, right? We would just deduce our probabilities. And that's going to be a key point. But suppose it looks something like this. It'll look something. It'll have some shape. It'll have some form. It'll be like this. And it'll be a discrete and finite set. Anything that actualizes, anything that takes a value, will take an actual value, even if it lives on the continuum. All right, and the continuum is absolutely continuous, even if space, say, for instance, is absolutely continuous, which I think it probably is. When anything takes a value, it takes a value. It no longer has infinite possibilities. It takes a discrete value that's measurable or knowable, and it exists in a finite way. So we'll have a discrete finite thing, and this is just a histogram of whatever it's going to, whatever the eventual thing will look like. And every possibility will be here, every possibility, and they could be lots and lots of them. This is just a cartoon, right? And they could be very tiny differences between each of the histogram numbers and so forth. Even if we imagine n growing very, very large, it'll still be a finite and discrete histogram like this. All right, now, if you had a normal distribution as a model, and even though there's no probability leakage here because we're just assuming we can't deduce anything about this from other matters that tell us that this is necessarily going to be finite, for instance, or this is necessarily going to be finite going this direction, or we can't reason that out, or we're not really worried about it, or something, we're not thinking about the finiteness of this. So there's no obvious probability leakage. So, but we still have this. And there's still, we could draw our normal distribution over this, and that normal distribution will be wrong. because that normal distribution just has two parameters, that whatever we end up with right here will not be a normal distribution, because the normal distribution still lives on the continuum. All right, the normal distribution and any of the continuously parameterized distributions live on the continuum, or perhaps the half line, as I say, you know, from 0 out to infinity, or 0 to negative infinity, or in multi-dimensions of this same kind of a thing. So we're still giving probabilities to impossible events. This is still probability leakage. All right, because here we're imagining this is everything that's ever going to happen. And even if every one of these points lines up exactly on this normal distribution right here, we still have this gap right here. This gap could be very small indeed, but it'll still be a gap. And the normal distribution is still giving probabilities to that gap, which is impossible. So there is probability leakage after all. So the parameters cannot be true values of the parameters representing this thing. They can be a darn good approximation, true, but they will not represent the true thing that will eventuate. So that leaves one possibility. The possibility is if we have a model of something that we deduce from absolute first principles, like we deduce through philosophical arguments, I don't know if this is true, that space is absolutely continuous. In other words, it lives on the continuum, or perhaps something even higher than the continuum. There's layers of infinity, if you remember. The simplest counting one, and then there's cardinalities of the of infinities. We did this before too. The simple, 1, 2, 3 infinity, and then the real line, the continuum, and then there's higher infinities still. What about those? We virtually ignore those in probability because they're very hard to think about. They're very difficult to think about. But in any case, suppose we deduce from first principles. It doesn't have to be a normal distribution now. We have some distribution. It lives on the, whatever this thing is, like space maybe is absolutely continuous, only on the real line. We have deduced that. And then we, from first principles, deduce, not just ad hoc, not just throw out there or something like this, or find a model that was reasonable, we think, but we deduce from first principles what this model will be, this parameterized model will be. That might fit into this scheme. I know of no such model, though. I know of no such model that we're deducing from first principles. This model can have no constants in it, like the speed of light or something like that, which is not known to infinite precision. Okay, so you cannot say that that fits into a scheme like this. I know of no such models that are like this. But it exists the possibility, at least I haven't disproved it to my own satisfaction, that something like this would happen. And in any case, whatever we're going to do, if we're going to use this in science, which is talking about the measurable. Now, you might talk about such distributions in thinking about the Lord above or something like this, who is omniscient and omnipotent and so forth. Maybe there's something there, and I'm not saying there isn't. But in order to use this in science, whatever we're going to do, the continuum is a potentiality in an Aristotelian way of thinking about this. Actual values, their actualities are finite, always finite, even if incredibly large. Okay, so we'll always be back to this situation. So none of these models represent true parameters in those situations. And it's possible, again, I say, these parameters are real and do represent true things, but not in science. It would have to be, as people say, metaphysical or something like this. Okay, but that's not anything we're going to run into. Okay, next time we're going to do control, and then which isn't control, and then we'll do the Bayesian and other ways and things like this, the right ways. And we'll just continue on with models. We got a lot of things to say about the abuse of time series, and I don't want to say the word because then the algorithm will get me. But this field right here, and all the abuses of statistics for that, and in medicine and so forth. All right, that's it for now. Thank you for the questions. These are excellent questions, and it's probably much more information than you wanted, but we had to explore all the possibilities. Thanks for watching.